In this example, the notebook is quite instructive because it refers to a small data set. And I think working with small data sets are actually handy in the beginning when you are trying to understand what is going on. Here we have the classic case of dogs versus cats. We have also the simplest possible task in machine learning, which is classification, image classification in this case. And we are going to be using convolutional layers in order to detect, to classify the presence of a dog or a cat in an image, okay, or cats in this case. All right, so the dataset is available in Kaggle. The original dataset contained 25,000 images, but we have cut down to 1,000 images per class. And we have split the dataset into train and validation and test dataset. Okay, all right, so we are going to obviously use train and validation to create, if you like, our model. And of course, we are going to exercise some kind of prediction API using our test dataset after a model is created. So the architecture we're going to be using here is an architecture that we have kind of developed specifically for this example. Consists evidently of convolutional and interleaved with max pooling layers. And probably you recognize the API here. In this case is a kind of a Keras API. Similar architectures can be developed for PyTorch. The first layer over here is a convolutional layer. There is input images of 150 by 150 pixels. This is what the images that we have transformed now are. And each image is a naturally colored image of 3 channels, red, green, and blue. We have 3 by 3 kernels, and we have the 32 here indicates the number of filters, okay, or convolutional neurons. And we are going to be using a rectified linear unit. They're exactly the same non-linearity that we have used in the fully connected layers. Then we are passing the output feature map produced here. And by the way, this is where you can actually see the usage of that kind of formula, which I was pointing out regarding the output feature map dimensions in an earlier video. The max pooling layer in this case is 2 by 2, and it will further shrink the output feature map produced by the first layer, selecting the most important features out of it, passing it over to a convolutional layer with 64 filters. Here you see now the pattern of increasing the number of filters as the network becomes deeper and deeper. And at some point, after 1, 2, 3, 4 layers, 4 convolutional layers, we are going to have the head. And I think it's worthwhile going back into this VGG kind of architecture and look exactly where that head was in that architecture and couple it with this code. So here is the point where the head starts, and the head in this case is a concatenation of fully connected layers. Why we have this kind of concatenation and want to do just a single layer is, gradually, even within the head, we need to gradually reach this point of desired number of classes. We have a classification use case here. This is 1,000 classes that need to be present in at the top of at the end of this network, and this is basically the dimensionality of our posterior probability distribution. We're going to have a y hat, if you like, that consists of 1,000 numbers. 1,000 are also the number of classes in the ImageNet dataset. So these dimensions correspond to the ImageNet classifier dataset. And so that's basically our head. There is also seen over here in this code with this portion of the model. So we have whatever we have produced in terms of convolutions over here, and then we flatten the network. So we flatten the output feature map there. By flattening the output feature map, we're creating effectively a volume. We're taking a volume at the input and we're flattening into a vector. And this vector then is passed as input to two dense layers. The first dense layer has 512 neurons. It takes whatever dimensionality, and we'll see now the dimensions in a moment, the flattened layer provided, and reduces that, just like any fully connected layer we have seen in a corresponding video in a different video earlier, into 512 dimensions, and we use the rectified linear unit for that. And then the subsequent layer takes 512 dimensions and reduces it further into a single dimension, because as we have seen in the binary classification, we have a binary classification use case here. Either we're going to have a cats or dogs. We have just a scalar that we need, because that is the probability of the positive class, whatever that positive class is, probably the dogs here. And we are, of course, going to be using sigmoid, because only at the output of the sigmoid we are actually getting this form of the posterior probability, as we had discussed in the fully connected layers and in that lecture. All right, so this is basically our architecture. Very simple architecture. The convolution portions, the flattened and the fully connected or dense portion to provide the binary classification result at the output. And here is the details of our CNN. So we can see the input images that are actually were coming in. First, we have 32 filters, as we discussed. In terms of number of parameters, 896, 18,000, 73,000, 147,000. So all of these are parameters that you see being quoted here in the next to the convolutional layers. But the most striking thing over here is this. Look at the number of parameters which are involved in a fully connected, in one fully connected or dense layer. 3.2 million parameters. So out of the total 3.5 million parameters that we have, 3.2 million are associated with a fully connected layer. And here is the kind of striking example of why it would make sense to actually use CNNs for image classification. If we didn't have the CNNs and the associated advantage of that CNNs provide, which was actually also shown in this kind of snapshot architecture, as you can see, only the local pixels, the one which are local to the spatial dimensions of the filter, are so-called firing in order to produce that kind of scalar. Okay, as compared to a fully connected architecture where everything that we have here is going to be connected to the layer to form, if you like, the output scalar Z. The convolutions operation is actually helping us to significantly reduce the number of parameters. So at the end of the day, we have the scalar that indicates the posterior probability of the positive class, as we discussed, and then the architecture seems to be valid. We are evidently going to use binary cross entropy, just like what we have done earlier in that other video where we looked at dense layers only for binary classification or multi-class classification. And we are going to have here, well, here the author selected the RMS prop, which is one of the cousins of stochastic gradient descent. We haven't really got any discussion specifically on enhancements of stochastic gradient descent, but if you do replace it with SGD, I think you will be getting very similar performance with the corresponding learning parameter. And then, of course, the metric is our accuracy. And one of the things that we would like to point out in this kind of convolutional networks is that we will need to be careful when we first take a data set and we try to process the images. As we have seen, the images are typically given to us as with pixels corresponds to integer numbers, so we have to definitely normalize them We have to batch them. We have to do a lot of this kind of transformations in order for us to produce the right inputs for the for our network. So after a training process that involves multiple epochs, as we would expect, we have a model, and we can actually plot the training and validation loss, as well also the corresponding kind of accuracy, and look at the corresponding loss over here plot as the number of epochs. And remember what we have said in another video regarding the condition of overfitting. And at that time, the discussion was an example of a linear model on the regression task. Over here, we have a classification task, but the sort of problem of overfitting is present in across tasks in machine learning. So we see some quite significant difference between training and validation as the accuracy is improving. And that is really what we have said earlier as a good indicator of overfitting. Okay, so it seems that the network that we have designed over here overfits the data set we are given, and it shouldn't be a complete surprise to us given the fact that we are throwing a significant number of parameters in a network, in a data set which only has 1,000 labels per class. So we can actually engage any of the techniques that we have seen in overfitting to address overfitting, such as weight decay, any of the regularization techniques that we have seen also in neural networks to address it. But in computer vision, we have something else that could actually help us, and this is actually called data augmentation. So I think it's worthwhile going through the data augmentation, because it is really a fairly straightforward and widely used approach to avoid a situation such as this where we have overfitting. So in data augmentation, what we actually do, we are taking the input images, and given the fact that we have the knowledge of the class, we try to transform these input images in creating more data. So that's an artificial way of increasing the number of labels we have in our data set. Via various kind of transformations, we may be shifting or rotating images, we may sharing the image, we are zooming in, zooming out, and flipping, and so on. We are definitely going to be creating some nasty cats or dogs, but definitely this helps our network to not overfit. And so if you are to just keep exactly the same network architecture as we have seen earlier, not touch at all the model, but definitely train the model with this additional kind of data set, then look what happened. We have a training and validation loss which are very close to each other. So we actually have solved the overfitting problem, and our accuracy is both in terms of training and validation are also very close, and close to something like 85%. Okay, so I think this is a good example to showcase the CNN models as working for the simple task of image classification. And what we actually also would like to understand now next is what we have said earlier about, how can we have some kind of visualization into the internals of the CNN to understand what is actually learning. And this is what we will be discussing next.